This is part 2 of a 2-part series where we prove the existence of angle pairs, where each angle in the pair has the same value, and where the angles result from having a pair of parallel lines and a diagonal that's called a transversal intersecting both of the lines, which results in 4 angles on each intersection. Each angle in a pair sits separately from the other angle. These pairs come in 2 forms. The form we looked at in part 1 is called an alternate pair, otherwise known as alternate angles, where the members of the pair sit on opposite sides of the transversal. Now in part 2 we're going to discuss the pairs that are called corresponding angles. The difference in these pairs is that each of the pair sit on the same side of the transversal, either the right side as you can see in the top 2 examples, or the left side as you can see in the bottom 2 examples. And we're going to prove why for each of these pairs, both of the angles have the same value. So let's begin with the basics, just the 2 parallel lines and the transversal intersecting them. And I'm going to add the first pair of angles and claim that these are corresponding angles and they have the same value. After we've proved that this is true, the other 3 pairs will be much easier to prove. I'm now going to add in 2 extra lines that are perpendicular to the parallel lines. One on the right which cuts through the top intersection, and the other line which begins at the point where the transversal intersects the bottom parallel line and just goes straight upwards. Now because the original lines are parallel, the distance between them remains constant, and because the 2 new lines are perpendicular to the original parallel lines, they must be parallel to each other, and therefore the distance between them remains constant, and this creates a quadrilateral where opposite sides are equal. I'll label the height of this quadrilateral A and the width with B. Notice that the transversal creates a diagonal cut through this quadrilateral, and that results in 2 triangles. When you have a quadrilateral with parallel sides, if you draw a diagonal through opposite corners of the quadrilateral, the result is 2 identical triangles. And you can see that they're identical because each triangle has the edge B for the base, A for the height, and they share the remaining edge, which is a diagonal. And the triangles being identical is going to help us see why the red angles are identical. Now if you look at the top red angle, you can see that it is a composite angle. Hopefully you can see that the right side of the composite is a 90-degree angle because it's formed by 2 lines that are perpendicular to each other. And then this is a remaining angle whose value we don't know. And notice that the unknown angle is also within one of the triangles, the triangle on the right hand side. I'm going to give that angle the value of x. But notice that the angle x is opposite to the triangle edge B. But because these 2 triangles are identical, then in the triangle on the left hand side, the angle that's opposite the edge B must also be x. Now if we focus on the quadrilateral, we can see that these 2 angles are within the quadrilateral, and there's another angle adjacent to each of these angles within the quadrilateral. Now if we focus on one of these angles for the moment, the bottom one, you can see that these 2 angles are composite angles within the quadrilateral. Together they form the corner angle, which means their sum must be 90 degrees. That must mean that the value of the unmarked angle is 90 minus x. So this angle is 90 minus x. But if you focus on the transversal, let's highlight that in a different color so it stands out. You should be able to notice that this angle 90 minus x is adjacent to the red angle, and they're both sitting on the transversal. And if you ignore the x angle and consider the fact that the transversal is a straight line, the 2 angles make up the angle on that straight line. The sum of angles on a straight line is 180 degrees. So the sum of these 2 angles, 90 minus x, and the red angle must be 180 degrees. And that can only mean that the red part of the composite angle must have the value of 90 plus x, because the sum of these 2 angles is 90 plus 90, and then the x's cancel, which is 180 degrees. So the red angle must have the value of 90 plus x. But now if we look back at the top red angle, we know that it is composite and it is made up of x and 90 degrees. So this angle also equals 90 plus x. And so we demonstrated that these 2 angles, which are on the same side of the transversal, have the same value. Therefore, they are corresponding angles. Now that we have the first pair of corresponding angles, it's going to be much easier to prove the other three pairs of corresponding angles using this pair that we've just proved. Now there are angles that are adjacent to these two angles to the left. Now the first angles and these second angles are adjacent, and they're angles on the parallel lines, which themselves are straight lines, which means the sum of the red and lilac angles must be 180 degrees. But we just saw the value of the red angles, which was 90 plus x, and so the value of the angle adjacent to it must be 90 minus x, and when you add these two values together you get 90 plus 90, which is 180, and then the minus x and plus x cancel, so the sum of these two angles is 180, which confirms the value of the new angle is 90 minus x. And of course, because both red angles have the same value, both the new angles must have the same value, and that's the second corresponding pair. I'll display the pairs on the left so that we know which ones we've already proved. The next pair of angles we're going to look at are the ones that are adjacent to and on top of the red angles. Now again, if we consider the bottom adjacent angles, if we highlight the transversal again, we can see that the red angle and the new angle are sitting on the straight line of the transversal. They make up the angle on the straight line. Their sum must be 180 degrees. And by now you should have worked out that the value of the blue angle must be 90 minus x. You'll get 180 degrees if you add those two angles. And because both the red angles have the same value, the other blue angle adjacent to the other red angle must also have the value of 90 minus x. And so that's a proof for the third pair of corresponding angles. And now we just have to prove the final pair. In order to do that, let's go back to the pair that we proved before this one and show its value. Now we know the value of both blue angles is 90 minus x, the value of both red angles is 90 plus x, and the value of both lilac angles is 90 minus x. That has to mean that the value of the remaining angles, which are on the top left of each intersection, must be the same. So the orange angles must be a corresponding pair, and so our proofs are complete. By the way, angles around parallel lines and a transversal can be used to prove the properties of different shapes, such as parallelograms and triangles. I've made a few proof videos using the properties of parallel lines and transversals, and they're linked in the description in case you're interested in seeing how we can use these properties we proved today in determining the properties of other shapes. Well, that's it for now. Thanks for watching.